For years, we've been warned about the potential dangers from the sun. Powerful eruptions of radiation and plasma can strike Earth, supercharging our atmosphere and magnetic field, essentially hitting a global reset button on our technology. A strong enough burst could cause a geomagnetic storm, knocking satellites out of orbit, disrupting internet-carrying submarine cables, and causing massive blackouts by collapsing power grids. Just a few days ago, one of the strongest solar outbursts in 20 years hit our planet. These solar storms disrupt power grids, GPS systems, and high-frequency communications in some areas. This activity suggests that the solar maximum, the peak of the sun's 11-year cycle, might come sooner than expected. As the sun's magnetic field flips, we should brace for more geomagnetic storms in the coming months. While these storms could lead to spectacular auroras, they also pose a threat to radio communications and electrical infrastructure. So what exactly happened on the sun's surface to cause this geomagnetic storm? How did it create such a stunning light show 150 million kilometers away? And most importantly, what will happen when the Sunspot group faces Earth again in 2 weeks? Stay with us till the end of this video to know more. The recent solar storm was caused by the Sunspot group AR3664. Sunspots are dark, cooler spots on the sun's surface. Their center temperatures range between 3,000 and 4,500 Kelvin, cooler than the surrounding areas, which are about 5,800 Kelvin. AR3664 rotated into view from Earth a few days ago. Initially, it appeared normal, but then rapidly expanded to 16 times the width of Earth, spanning 200,000 kilometers. It became one of the largest sunspots of this solar cycle. At the start of the month, NOAA's Space Weather Prediction Center warned of increased solar flare activity from AR3664. The sunspot lived up to expectations, emitting 75 M-class and 10 X-class flares in a week, accounting for 50% of this year's X-class flares. A solar flare is a sudden, intense burst of radiation on the sun, visible as a bright flash. These flares last from minutes to hours, releasing immense energy. The light reaches Earth in 8 minutes and 20 seconds. Flares are ranked by strength: B-class, smallest, followed by C, M, and X, strongest, each class 10 times stronger than the last, and each divided from 1 to 9. C-class flares usually don't impact Earth much, but M-class flares can cause short-term radio blackouts and minor radiation storms, which can be risky for astronauts. Solar flares are often confused with coronal mass ejections. A CME is a massive cloud of magnetized particles ejected into space when the sun's magnetic fields realign explosively, traveling over 1 million miles per hour and taking up to 3 days to reach Earth. Unlike solar flares, CMEs are huge clouds of gas expanding into space. When a CME hits Earth's magnetic field, it drives particles towards the poles, creating auroras. Both phenomena arise from the sun's magnetic field realignments, but they differ in emissions, appearances, travel methods, and effects on Earth. Solar flares appear as bright flashes, while CMEs are vast clouds of magnetized particles. The solar activity began to rise on May 3rd with an X1.6 flare. Within 48 hours, 2 more X-class flares were observed. The next day, the sunspot emitted an even larger X4.5 flare. The first CME was observed on May 6th. On May 8th, another CME followed an M8.6 flare. On May 9th, 2 X-class flares produced 2 more CMEs. By May 10th, 4 CMEs were heading toward Earth. Scientists believe the last 3 CMEs merged into a Cannibal CME due to their different speeds and overlapping paths. When a CME reaches Earth, the magnetic field deflects the storm, creating a funnel where gas streams down at the poles, resulting in daylight auroras. The magnetic fields stretch back, break, and gas streams along magnetic lines to the poles on the night side, creating nighttime auroras. Auroras are usually green, but during strong storms, they can turn red. The color differences depend on the particles involved and the altitudes where they interact. Blue and purple auroras occur when solar particles interact with molecular nitrogen up to 62 miles. Green auroras form when particles interact with oxygen at 62 to 186 miles. The striking red auroras appear during intense storms when interactions happen with oxygen at higher altitudes of 186 to 248 miles. Red auroras need to be exceptionally bright to be seen with the naked eye, at least 10 times brighter than green auroras. Geomagnetic storms can significantly affect electrical power grids and satellites. During these storms, geomagnetically induced currents can flow through power lines and transformers, causing them to overheat and potentially fail. Solar activity, particularly from large sunspots like AR 3664, poses significant risks to modern technology and infrastructure. Geomagnetic storms triggered by solar flares and coronal mass ejections can induce geomagnetically induced currents, GICs, in Earth's power grids. These currents have the potential to overload transformers, trip protective equipment, and damage generators, leading to widespread blackouts and disruptions in electricity supply. Historical events, such as the 1989 Quebec blackout and the 2003 Halloween storms, illustrate the real-world impacts of solar storms on power grids and technological systems, including satellites and communication networks. Today, our reliance on advanced technology and interconnected systems makes us more vulnerable than ever to solar disturbances. A major solar storm, akin to the Carrington event of 1859, could lead to economic losses estimated in the trillions of dollars due to infrastructure damage, prolonged outages, and disrupted communications. Protecting against such events requires proactive measures, including improved space weather forecasting, robust infrastructure design to withstand GICs, and emergency response plans to mitigate the social and economic impacts. By recognizing the potential risks and investing in preparedness, governments, industries, and researchers can work together to minimize the impact of extreme solar events on our increasingly technology-dependent society. Now you know how much damage these storms can cause, so do you think our governments and us are equipped with enough knowledge and infrastructure to tackle such situations when it happens again? Can we minimize the loss as low as we can next time when these kinds of solar storms hit the planet, and not just merely hope for the storm to become more intense? Let us know your thoughts in the comments section below. And if you find this video informative, then do like it and subscribe to our channel for more knowledgeable content on space science.